In this ECCV workshop on computer vision in the wild, there are two challenges. For image classification in the wild challenge, there are 4 tracks. For object detection in the wild challenge, there are 2 tracks. There are 6 tracks in total, and a 5-minute talk will be presented for each track. Here's the presentation in the industry track of the image classification in the wild challenge.
Hi, this is Junyang from Damo Academy Alibaba Group. It's my pleasure to be here to present our work to you. This work is called DetCLIP, which is a language image contrastive lens-based pre-trained model on Chinese data. It is also a participant in image classification in the wild. Firstly, we collect a large-scale data of image text pairs in Chinese. We applied contrastive learning for pre-training. As to the pre-training data, we try to make it as public as possible so that you can re-implement it in our way. It consists of Chinese data in Lion 5B, Wukong dataset, and some classical datasets like Visual Genome and Coco. We translate the text into Chinese with our internal tool. As to the pre-training method, we apply 2-stage pre-training. In the first stage, we use locked image training, which freezes the parameters of the image tower. This is because we use the initialization of clip width and Roberta Chinese. So in the first stage, we pull the representation of the text encoder closer to the successful clip width. And then we unlock the parameters and make them more trainable so that the pre-trained model can adapt to the knowledge of the Chinese data. In detail, we have trained 5 sizes of Chinese clip, including ResNet 50, width base, width large at 336 pixels, and the largest one, width huge. In this competition, we have done some specific work, including translation for labels and manual prompting. As the text in the datasets are all English, we need to first translate them to Chinese so that we can adapt Chinese clip to the zero-shot classification. Some can be translated directly, like birds, cats, and something more general concepts. But some need searching for background knowledge for the most proper ones, which are quite difficult, like the names of cars and the names of planes. And in some cases, we use different words for the same meaning, and we can achieve better results. As to manual prompting, we apply prompt ensembling as is done in original OpenAI clip. We found that the translation of OpenAI prompts perform most stably across datasets in comparison with the provided prompts. We translate the prompts into Chinese manually. As to the results, you can check our results in the leaderboard, including the width huge and the width large, and also we have some results of width ResNet 50. So you can find that with an increase in size, the models can increase the performance stably, and width huge performs the best. And you can find that width huge performs quite well in some datasets like Cypher and also like VOC. So for the general concepts classification, it can perform well for Chinese clip, but for some datasets which are mostly about the Western culture, like food 101, which are mostly food in Europe and America, and something like Stanford cars and planes, it is quite hard for a Chinese clip to perform very well in these datasets. But generally, we can find that larger models and longer pre-training can make Chinese clip also perform very well on these datasets. And Chinese clip also has the ability to perform well in zero-shot image classification. Additionally, we have provided some other results for comparison, including results in cross-model retrieval, including e-commerce image retrieval, general domain cross-model retrieval. Chinese clip can perform stably better than the baselines, which are the solar models, Chinese multi-model models in this year. We also built a demo internally, which will be public soon. You can find that it can retrieve the related image as well. Like the query is 2 dogs playing on the snow. You can find 2 dogs playing on the snow and green apples on the table. And this one is quite interesting, which is a dog which looks like a zebra. So you can find some black and white dogs. And an interesting prompt like a cat wearing shoes. You can also find that a cat inside a shoe or a cat really wearing shoes. And also it can retrieve some paintings like an oil painting of a running horse. So that's it for my presentation. And thanks for your listening. If you feel interested in our work, feel free to contact me to this email, and you can follow our GitHub to follow our latest updates. Thanks very much.
Here's the presentation in the academic track of the Image Classification in the Wild Challenge.
To introduce our new work, K-LITE, how to train generic view backbone by leveraging external knowledge, and how will that help image classification in the wild. Let's start by reviewing existing research and current trend. Zero-shot learning has been studied for at least 1 decade in our computer vision community. Most research investigate how to build model to generalize to unseen object categories in single domain. For example, device. I will call this traditional setup class-level transfer. Thanks to recent advances in vision language pre-training, we have observed a clear trend by moving from class-level transfer to task-level transfer. For example, CLIP. It was trained on over millions image text pair and then evaluated model performance on over 30 image classification dataset. For class-level transfer, our community has produced a rich line of research for modeling. It essentially wants to associate seen and unseen concept with some auxiliary info, such as implicit knowledge in pre-trained model or implicit knowledge in knowledge bases. And we want to borrow the idea of leveraging this external knowledge for vision and language pre-training as well, so that produce our recent work K-LITE. I will start with motivation example. Leveraging external knowledge as a common approach that a human being use to make visual recognition decisions in our daily. Imagine the first time we are in a Japanese restaurant. We are offered a menu with dish names only. It is very hard for us to understand what they are, not to recall their visual appearance. After the waitress explained the concept using her knowledge, we may immediately have a better idea of the dish and therefore order the correct dish we imagine. You may have seen this. Instead of trying to memorize all the concepts, we humans leverage structured knowledge to efficiently adapt to new settings. Similarly, we want to borrow the idea for vision language pre-training, as external knowledge is generally available in many domains, such as databases and textbooks, and we want to build a systematic and generic approach to leverage external knowledge for task-level transfer. K-LITE is one recent effort we tried. Most existing vision language pre-trained models are trained with image text pairs. This is the baseline we consider. In K-LITE, the language side is enriched with external knowledge. It first constructs queries, use entity extraction techniques, then retrieves the related knowledge from knowledge bases. The retrieved knowledge will be used as additional supervision for image text learning. Therefore, we are training vision language pre-trained model based on 4 data spectrum, image language knowledge, instead of image language only. The same knowledge augmentation process is applied to both training process and evaluation process. We apply this technique to both image classification and object detection. For image classification, we use UniCell as a baseline pre-trained method. We evaluate the model performance with zero-shot and few-shot performance on ImageNet 1K and ICinW. The average score I reported. K-LITE is more sample efficient than UniCell. It shows comparable performance using only a half number of training image text pairs. We provide breakdown analysis result for 20 image classification datasets. It improves zero-shot performance on 17 datasets. While it turns out fine-grained image classification tasks benefit the most from external knowledge, and knowledge may hurt the performance when the quality is low. For example, it includes additional concepts that confuse the model. When adding external knowledge for DetCLIP pre-training, it also improves object detection on both levels and certain downstream datasets. Evaluate with zero-shot task transfer. When scaling data to largest academic dataset and model to string-based, K-LITE achieves the top performance on zero-shot academic ICinW challenge, which improves UniCL by 2.27. More details could be found in our New Year's 2022 paper. Thanks everyone.
Here is the presentation in the ImageNet 1K in pre-training track of the image classification in the Wild Challenge.
Hello everyone, thanks for watching this video. Today I would like to introduce our work Bamboo Building Mega Scale Vision Dataset continuing with Human-Machine Synergy. My name is Yuanhan Zhang. I'm from SLab NTU, Singapore. The VIT-B60 model pre-trained on Bamboo achieves very good performance on the computer vision in the Wild Challenge image classification track. Now let's introduce why and how we build these datasets. The current construction of computer vision datasets mainly include two dimensions, label system and data annotation. Label system decides the overall diversity of your datasets, specifically how many categories your dataset will include. And the efficiency data annotation strategy can ensure you can annotate the most number of images under the smallest budget. For label system, WordNet, for example, WordNet is a commonly used large lexical database of the English, which is used as a label system for many popular datasets like WordNet. Though it was large, it was built in 2006, so it did not include many new words like iPad. And also, as we know, WordNet lacks many fine-grained concepts like this one. It's kind of the bird. Second, for data annotation, the OpenImage as an example is the largest publicly annotated dataset. But the biggest problem for OpenImage is its data might not very benefit to the society. What is this means? This means, for example, as COCO is a very good detection dataset for 18 common concepts. So why OpenImage also spend a lot of budget on concepts that COCO already carefully annotated, right? So for Bamboo, Bamboo just aim to build a new dataset which cover more concepts, more diverse concepts, and ensure the new annotated data benefits the society at the most. First, how to extend WordNet. It is very important to get a much larger label system, right? So based on the WordNet, we collect the concept of current public dataset and further extend it through another knowledge base, Wikidata. And we use three solutions to integrate this new concept into the hierarchy tree of WordNet. And these three solutions is used in parallel. Second, based on this diverse label system, how to ensure the new annotated data is beneficial to the society. The first step is we unify the 24 public datasets, and we analyze the distribution of these datasets. Then we annotate new data based on active learning. The model for active learning is trained on public data first. Based on the uncertainty of the model prediction, we can only annotate the web data that the model is uncertain, its category, or the data that is not included in the current dataset. Based on this strategy, we can ensure that new annotated data is an addition to the public dataset, which is beneficial to the current society at the most. Based on this active learning strategy, we built Bamboo datasets. The Bamboo classification part was 4 times that of ImageNet, and the Bamboo detection part was 3 times that of the Object 365. Besides, as we said, the newly annotated data is a huge addition to the distribution of the existing academic data set. We can set the new annotated data is mostly at this part. This part is the concept which never showing in the current data sets. Okay, let's see how the model pre-trained on Bamboo performs. In its challenge, on the ImagineNet 1K in the pre-training track, the Bamboo pre-trained VIT B16 model achieves best performance. With the same model design, the VIT B16, on the full short setting, Bamboo helps the VIT B16 model gain 3.18 points over the same model pre-trained on ImagineNet 22K. And on the full short setting, the improvement is more significant. When we analyze on the performance on datasets wise, we can say that the performance gain mainly comes from the data domain that the Imagine 22K rarely includes, such as aircraft, food, and cars, which further indicate that the new annotated data in Bamboo is a huge addition to the character distribution of the existing academic datasets. You can just explore and download Bamboo data at this website, and you can try to download our Bamboo pre-trained model on this website. Finally, you can try to play Bamboo pre-trained model on the Hugging Face. Okay, thanks for listening. That's all my presentation.
Here is the presentation in the parameter efficiency track of the image classification in the Wild Challenge.
Hello, everyone. I am Yuning Liu from University of Science and Technology of China. I am happy to present our work, ProDA, Prompt Distribution Learning on the ECCV workshop. This work was done during an internship in Huawei NO's ARC Lab. Recent progress in pre-trained vision language models, such as CLIP and Align, provides a promising opportunity to explicitly leverage human language for addressing downstream recognition tasks efficiently. A pre-trained vision language model can effectively address various tasks with the provided natural language. During pre-training, vision language models learn aligned embeddings of image and text via contrastive learning, encouraging the representations of an image and its language description to be similar. In the downstream task, providing the task-related content, for example the category descriptions, can significantly benefit the recognition even to perform zero-shot inference. Existing works generate category descriptions from handcrafted prompts, such as a photo of. The recognition performance of vision language methods is highly sensitive to the form of the provided content. However, it is still a challenging problem to determine the optimal text descriptions. One challenge arises from the diversity of visual content. Due to inherent factors such as pose, deformation, and lighting conditions, there exists significant diversity among various examples within a category. This intra-class variance prevents a prompt from sufficiently describing visual variation. The prompts are desirable to be diverse and informative, allowing to handle the variance of visual representations. On the other hand, the prompts are specific to each problem. A default prompt is a photo of, which works well for generic object recognition. However, it is difficult to handle fine-grained object recognition. On the flower dataset, a better choice of prompt is a photo of a type of flower. In this case, the word flower indicates the context of the current task, thus providing a more precise description. The provided text should be adapted to the task-defined context, that is, low bias to the visual representations of the target task. Despite interesting results of handcrafted prompts, manually designing introduces artificial bias and could be suboptimal for the target task. Thus, customizing suitable prompts for different tasks relies on repetitive and time-consuming attempts by experts and also requires a large validation set for prompt selection. In this work, we present prompt distribution learning, ProDA, as a data-driven approach for automatically learning diverse and low-bias prompts from data. Given the purpose of learning the prompt distribution, the challenge is how to perform the learning efficiently. Considering the soft prompt as a sequence of tokens, precise modeling relies on a complicated sequence generation model, requiring a large number of target samples for training. We adopt an efficient solution that learns the distribution of the output embeddings of the prompts, with class names, that is, the weights of the classifier, instead of learning the distribution of the input embeddings of the prompts. As shown in the figure, Although the various descriptions within a category are significantly different in the raw text, or low-level embeddings, the high-level embeddings are usually adjacent. We can use a simple distribution to model them, such as the multivariate Gaussian distribution in our work. Specifically, we maintain a collection of learnable continuous prompts. The mean and covariance of the weight distribution can be estimated from a series of classifier weights, which are generated by the prompts from the collection. However, even with the Gaussian distribution assumption, the exact computation of the marginal likelihood is still intractable in the multi-class case. To address this problem, we derive an upper bound of the loss for efficient optimization. To improve the diversity of prompts, we explicitly differentiate the prompts on both positions and semantics. At last, we show the results of ProDA on challenge of the image classification in the wild. As shown in the table, our method ProDA has the best accuracy efficiency score on the few-shot parameter efficiency track. Linear probe is a strong baseline in few-shot image classification. The comparison with linear probe demonstrates the benefit of prompt learning. It is noteworthy that ProDA uses the mean of classifier weights for inference, which allows our method to have no additional computational in the test compared with the linear probe. In comparison to the handcrafted prompts, ProDA is able to improve the recognition performance with few training samples. Compared with fine-tuning, ProDA has higher accuracy with extremely few trainable parameters. More details could be found on our CVPR paper.
Here's the presentation in the zero-shot track of the object detection in the wild challenge.
Hello, everyone, my name is Jianhua. I'm from NOAA ARCS Lab. Today I will give you an introduction about our paper named DetCLIP, Dictionary Enriched Visual Concept Paralleled Pre-Training for Open World Detection. Firstly, we want to talk about the motivations. That is, the most state-of-the-art object detection methods can only recognize and localize a predefined number of categories, which means they rely on sufficient training data for each category and require expensive and time-consuming human annotations. However, existing publicly available detection datasets only have a limited number of object categories. On the other hand, image-text pair data are cheap and abundant on the Internet. Recent vision language pre-training methods utilize those data to extend their open domain capacity and have shown good zero-shot ability on various downstream classification tasks. Therefore, we focus on building an open-world detector, which can utilize multiple sources of datasets to pre-train. We first introduce the main architecture of DetCLIP. DetCLIP is constructed based on a ATSS detector where the classifier is replaced by concepts text embeddings extracted from a text encoder. To enable an effective learning with a hybrid supervision from different datasets, we propose two core techniques: parallel formulation and concept dictionary. To unify the training process for different type of datasets, we propose a paralleled formulation where the concept noun phrase for each bounding box are extracted and fed into the text encoder individually to obtain the corresponding text embedding. Note that we utilize a pseudo-labeling procedure to transfer the image-text pair data into grounding data. For the concept dictionary part, we think that the existing detection, grounding, image-text pair datasets have a very large domain gap and difference in their labeling space. For example, a boy can be annotated as man, child, or people in the different datasets. There often exists hierarchical, inclusive relationships between different concepts. Knowing these implicit relationships can effectively facilitate the pre-training. Therefore, we propose to build a large-scale concept dictionary to provide the external knowledge from multiple sources. 1. Noun phrases extracted from the large-scale image-text pair dataset. 2. Category names of existing public detection datasets. 3. Object names from the manually collected concept database. Here is some illustrations of our concept dictionary. Based on the designed concept dictionary, we retrieve the definition for each input concept to provide the prior knowledge. Concept dictionary also helps to alleviate partial annotation problem for grounding and image text pair data, which is that only main objects that people care about are labeled in the caption. We alleviate this problem by adding negative samples for grounding and image-text pair data and introduce label completion for pseudo-labeling on image-text pair data with every concept in the dictionary. Observe from the right part of the figure, the use of concept dictionary helps produce higher quality pseudo-labels. For the experiment part, the DetCLIP outperforms the state-of-the-art GLIP by large margins on large-scale open world detection benchmark LVIS with 1203 classes. Our DetCLIP-T outperforms GLIP-T by 9.9% map and obtains a 13.5% improvement on rare categories. Compared to previous work GLIP, DetCLIP uses a lighter backbone and trained with less image-text pair data. DetCLIP is 5 times faster in training and 20 times faster in inference. For the ablation studies, the following table demonstrates the effectiveness of 2 core components of DetCLIP: the paralleled formulation and the use of concept dictionary. We construct the following table to study the impact of the scale of the proposed concept dictionary. It can be seen that using a small-size dictionary can even bring a performance drop compared to without the dictionary, while scaling up the dictionary with nouns from YFCC can significantly improve the performance. Here is a demo video of our DetCLIP. The proposed DetCLIP has achieved the best performance on ODinW challenge in ECCV 2022, with a 24.9% average performance. And more details can be found in our paper. Thanks for your listening. That's all for this paper.
Here's the presentation in the full shot track of the object detection in the wild challenge.
Hello everyone, I'm here to introduce our solution in OD in the wild challenge, which is named DINO. I will first introduce our model and then show our results in OD in the wild challenge. DINO was once the first place on COCO detection leaderboard. We can roughly divide the development of COCO detection methods into 4 stages, which are breakthrough, algorithm improvement, NAS, and transformer with pre-training. Recently, with the success of transformer on vision tasks, there comes DITR, a detection model with transformer head. Our DINO is the first DITR-based model, ranking top on the leaderboard, which shows a huge potential of fully transformer-based model on detection tasks. We mainly propose 3 improvements in our model, which are contrastive denoising training, look forward twice, and mixed query selection. In contrastive denoising training, we have 2 types of noise boxes, which are positive examples with small noises and negative examples with large noises. For example, the red box here with solid line is a GT box. The red box with dashed line is a positive example, and the yellow one is a negative example. We let the positive to predict the GT box and the negative to predict no object. This contrastive way reduces duplicate boxes. We also propose a look forward twice way for box refinement. The original way to refine box in deformable DITR is called look forward once here, in which each decoder layer approximates ground truth box individually, while trying not to influence its previous layers by stopping gradient. Such a parameter update approach is a graded way, which cannot obtain optimal. We propose to only allow the layer I to be influenced by gradients from itself and layer I+1. In this figure, we can see that in early layers, look forward once performs better. But in later layers, look forward twice performs better. This observation verifies our intuition that look forward twice sacrifice performance in early layers to achieve better final performance. We also propose mixed query selection and adaptive DN groups. For mixed query selection, we only use selected anchor box in the query selection part. We'll use learned embeddings as the content queries. For adaptive DN groups, we propose to use adaptive number of DN groups to guarantee that we have equal total number of DN queries. In this figure, we can see that our model have smallest model size comparing with the other sort models, and we perform best.
DINO reached impressive performance on the total object detection benchmark. We are interested in its performance on long-tailed data size. Hence, we take participating in the challenging object detection in the wild competition. The results are also promising. We got the first places on both full shot and few shot settings in the competition. Our model obtained 66.7 AP on the full shot benchmark, introducing 1 AP gains compared with the run-up. Also, on the few shot benchmark, our DINO outperformed DetCLIP T with 2.3 AP gains. This is the training menu here. We pre-trained our models on Object 365v1 for 36 epochs and fine-tuned the models on separate data size. We leveraged the swing transformer Tiny as our backbone and used the 4-scale features for the default setting. We have tried another training strategy. We merged all 35 datasets to a single dataset and trained one model for all images. Interestingly, the merged trained model's AP is slightly lower than separated results. That's our solution, DINO. Our code is available on the GitHub now. For more details about our solutions, please refer to the code and papers link below.
Hello, everyone. So if you are still here, this morning section is finished. Feel free to leave and go to the lunch. We will be back at 1:30.